explore the idea that to construct a good volume, a good map, you need good 2D classes. But having good 2D classes doesn't imply that you will have a good map necessarily. There are many things in between that can go wrong. So let's start. We have taken the particles taken from Empire 10005. That is this dataset. It is TRPV1, and it was given a resolution of 3.2 angstroms or 3.3 angstroms, and we took these particles and processed them. Not here, this, and process them in different ways. So the first thing is to analyze the 2D classes. So the 2D classes, this is an old data set, so we will not reach very high resolution. So even this 3.3 is a little bit questionable, but still we see a lot of internal details of the structure, kind of secondary structure here. It is a membrane protein. We see it is embedded in a nanodisk, and yeah, so some of the classes, this kind of stuff is always like this. So we have asked for 50 classes, and most of the particles concentrate in the most populated classes, but there are a few of them that always stay alone. So one particle, two particles. So the bad quality of these classes doesn't mean that the data is bad quality. So the data is good. So most of it is here, and then we construct different initial models, so or different maps. So they were given the angles. So from these angles we can reconstruct, and then we see that we reconstruct the correct structure, and we can check of it. We can check it in Chimera, and we don't see, for instance, here high dust, and then we can so here is the nanodisk, and then we can get rid of the nanodisk by so here we see the alpha helices, and well, that's fine, and this is how the structure looks like. So now we can construct an initial model without looking at the angles of this structure, and then this is the map that we get. So we are given a C4 symmetry as a constraint, and we get basically the same structure but at a lower resolution, and we can check it in Chimera. It is not exactly the same, but sufficiently similar. So we see same kind of details. Okay, so yeah, so sufficiently similar, and now I'm not refining this one. I just want to show that what you can do is you can do wrong structures, not that you can do good structures. I presume that you know how to do good structures. But for instance, let's say that here one of the important parameters is which is the maximum resolution that you use for the alignment. This is 12 angstroms. Here I have repeated the same process, exactly the same process, but I have changed just that number. So I have changed that number from 12 to 3. So if we think of in terms of here is the other one. So if we think of in terms of landscape, what we are doing is we are adding much more noise to the data, so the landscape of solution becomes more noisy and with many more local minima. So now first it takes longer. So this took 10 minutes. This took almost 4 hours. So, or more than 4 hours. And the structure that you getting here it doesn't seem to be correct. So we can, let's open it this way too. So there is a lot of details, but those are pretty artifactual. So actually we can try to hide dust. So there are a lot of details, but sometimes it is difficult if you don't know your protein. It is difficult to say this is a protein, this is not. At the level of slices, let's see if we can detect anything that looks like wrong. Should we open in there? Yeah, here it is. So the background is very black because yeah, the CryoSpark is masking the structure, but we don't see protein-like features. Actually, what we see here is rather artifactual proteins. Normally, they don't have these features. So I agree that you need a trained eye for this, but they don't. It doesn't look like a protein. And if you give, so that this is simply a manifestation that the algorithm has converged to a local minimum that is not the correct structure. And now if you take that map and refine it, it claims a resolution of 6.6, and if you look at the FSCs, they look good. Okay, and then if you look at the structure, at this resolution, because at this resolution we cannot see alpha helices, so 6.6 we cannot see alpha helices or beta sheets. Still we see something that should make us suspicious. So when you see this kind of let me enhance it. So for instance here, you see this kind of stripes coming out, this is a bad sign. This is a sign typically of misalignment. And so, but at this point, because we cannot see any details, we couldn't say this is a protein, this is not a protein. So you are bound to believe that this is the structure of your protein, but this is not. We know, because we have reconstructed in another way, and we know that this is not our structure. But otherwise, at this resolution, if you don't know the structure and you don't pay attention to these small details that indicate you that there is some problem, then you would think this is my structure here. So just a reminder of the summary. So if you don't have good classes like this one, so in these classes you have a lot of details. If you don't have these good details, you will not reach high resolution in your map. On the opposite, if you have the details, you still may not have a good resolution in your map, and the reasons can be various. So it can be a wrong initial model, like in this case, but it can also be that the protein is flexible, can be that you have multiple species and then you are mixing a few of them in the final 3D reconstruction. It can be that you have a good initial volume, but you are misplacing the particles in the angular space, and then you are making a wrong reconstruction. But having 2D classes is a must. So if you want to go to high resolution, you need to have good 2D classes. This would be all for this project.